Hello, my name is Cole Graham,
And I'm Caleb Mauck.
and we're going to be solving the case of the Tacoma Narrows Bridge collapse. I will be providing the narration for this video, while Caleb will be supplying the majority of our equations and our graphs that we will be using. On November 7, 1940, at approximately 11 a.m. Pacific Time, the Tacoma Narrows Bridge in Washington collapsed dramatically. Though there were no human fatalities, this day symbolized an engineering catastrophe of the third largest suspension bridge. The collapse was captured on film, thereby providing modern-day civil engineers the opportunity to further analyze the bridge's failure. The video capture is terrifying and breathtaking. Even to date, there is debate about its ultimate demise, but much of the engineering community attributes it to aerostatic flutter, the effect of a powerful wind speed of 42 miles per hour. The unfortunate event spawned a world of new scientific inquiry, prompting new research and mathematical investigations to prevent future collapses of bridges and other infrastructure. So let's begin. What you see here is a basic non-homogeneous second-order linear differential equation that matches a displacement of a spring from rest. Now, while the bridge is not necessarily a spring, what we're going to find out is that oftentimes it can behave as such. So, just for the first part of our investigation, let's assume that K and M, which would be the mass and the spring constant, are both equal to 1. And rather than setting b to a value, let's hold b as its own variable. And let's see what happens as we play around with b and we try and solve this differential equation with b remaining as its own variable. So let's solve that now. So after plugging everything in, we now have the equation in this format. Now, we know from solving these second-order linear differential equations, particularly this one, which is homogeneous, that if we have y equals e to the rt, then y prime must be equal to r times e to the rt, and y double prime, the second derivative, must be equal to r squared times e to the rt. So if we factor out an e to the rt, we wind up with a quadratic equation. Now, remember that we're keeping b as a variable. So this is what our roots will actually come out to look. And that's not too pretty, but when we go through and solve it, looking at the initial conditions, we find that we're actually going to have, at the value of 2, it's going to actually change our solution. Because if b becomes greater than 2, then you'll either have, in one condition, you'll have real roots, and in the other one, you'll have a complex root. So then we solve for those two equations, and this is the first solution that you get, and this would apply when b is greater than 2. And then if we move on a little further, we see that this is the second solution you get when b is between 0 and 2. Now remember, b is the damping coefficient, so it's not going to be less than 0. And we're used to it being a pretty small value close to 0, though. So we're actually going to, for the next part, which we're about to move on to, we're going to start with b at 0, and we're going to see what happens when we graph it using Desmos. So here for part 2, looking at that second solution that we found, when we graph it in Desmos and we start off with b equals 0, we can see a sinusoidal function with no damping, right? So this thing just repeats over and over and over and over. For a bridge, that wouldn't be too good. So look what happens when b is slowly increased, and we see how after 0, there's still a bit of a sinusoidal function. It's oscillating a little bit, except you see that it rapidly approaches y equals 0. So that is the damping coefficient in effect right there. Thus far, we solved the second-order linear differential equation as if it were homogeneous. But let's assume there were actually some type of forcing function. This would make it a non-homogeneous second-order linear differential equation. And let's say that the forcing function in question looks something like this: sinusoidal sine of alpha t. Now, we want to know, with this type of forcing function, what would the period look like and what would the frequency look like? Well, the period is simply 2 pi divided by b, which would be alpha in this case, which is that number in front of t. And then frequency is simply the inverse of period. So you have these two, period and frequency, and we see that as alpha increases, period decreases, and as alpha increases, frequency increases. So this is what would happen with a basic function like this when applied to the bridge as an external forcing function. For the next part of this problem, we're going to apply that forcing function to the original second-order linear differential equation that we had solved. This time, however, we're going to set b to 0, so we're not going to have the damping coefficient, and we're going to treat k as an unknown, the spring constant, and that's because that will affect the frequency of oscillations, and we wouldn't want to know that if we're going to be applying this sinusoidal forcing function. So that would give us an original equation that would look something like this. And as you can see, there's a y double prime term and there's a y term, but there's no y prime term. Now that we have this equation, we can use the same technique as we used in problem 1. So if we factor out the e to the rt, we're left with r squared plus k equals 0. And this is for the homogeneous solution. So if r equals, after using the quadratic formula, we come out with r equals 0 plus I times the root of k. So that means for solving the homogeneous second order linear differential equation, a will equal 0 and b will equal the root of k for a complex root solution. So then you are left with this equation right here. And this would be just the homogeneous. Well, we know from the extended linearity principle that the actual function y of t is equal to any homogeneous solution plus a particular solution. So now let's go and solve for the particular solution. So with the forcing function equaling sine of alpha t, we guess for the particular solution that it must be something like a times sine to the alpha t plus b times cosine to the alpha t, which would give us a first derivative of a times alpha cosine alpha t minus b alpha sine alpha t, and then a second derivative of negative a alpha squared sine alpha t minus b alpha squared cosine alpha t. And we know that there's not actually a cosine term in there because there is no first derivative, because we're having b equal to 0. So we already know from the outset that the value of b in this equation is going to be 0. When we plug in our values and solve with the initial conditions, we are left with a particular solution, as we see, once again, like I just said, b equaling 0 for this equation, but a is equal to 1 over k minus alpha squared. So here's our particular solution right here. We now combine the particular solution with the homogeneous solution, and then we once again plug in the initial conditions, and we solve for that again to find the values of k1 and k2. Once again, we see that k2, which would be the coefficient that would go in front of the cosine term, is actually 0. So looking on a bit further, after you look through this and see how the entire thing has been solved, we get to the final solution of this, which comes out to 2 minus alpha over the quantity of k minus alpha squared, n quantity, over, all of that over the root of k, and then that entire quantity times the sine of the root of k times t, plus 1 over the quantity of k minus alpha squared times the sine of alpha t. So already looking at this, we see that we're going to have two different periods and two different frequencies that are related to the root of k and alpha. And we're going to see what happens with that when we look into this further. Before we look at the solution in Desmos, let's just take a look at real quickly what happens to the period and frequency. So for the term with the root of k, sine root of k times t, see that the period will be 2 pi over the root of k, and the frequency will be the root of k over 2 pi. Similarly, if we look over here at the other term, we have sine of alpha t. So the period will be 2 pi over alpha, and the frequency will be alpha over 2 pi. Now, what would happen if k started to equal something like the root of a, or if a squared were equal to K. I wonder what would happen there. So let's go to Desmos and find out. Okay, so we're here in Desmos, and we see that starting off we have K, the spring constant, and then that A down there, that's just alpha. So just playing with a little bit, when we move K around, the oscillations happen faster and faster, and it looks like the amplitude's going down a little bit. Okay, now let's play with A a little bit, and let's see what happens there. Whoa, at A equals 1, the whole graph goes away. Well, that's because we would have a 0 under, we would have a divide by 0 term. So that's kind of strange. But keep playing with all of these. And, okay, there's more with A at 4. Let's bring it back down here. And, okay, well, we saw when it was 1, nothing happened. But, whoa, at 1.05, you got a big fluctuation. And it's almost like the opposite of a damping coefficient. So let's move K back to 1. And let's set A close, something really, really close to 1. And what happens? Whoa! So the whole thing explodes, still oscillating, except the amplitude is getting greater and greater. Basically the opposite of a damping coefficient. So what we saw is you had a divide by 0 term whenever K approaches alpha squared, or when the root of K approaches alpha. All right, well, that's kind of interesting. And we kind of played around with it. We had alpha equal to 0.9999, very close to K. But we actually want to figure out what this would look like mathematically as these values approach each other. So one way how to do that is by L'Hopital's rule. So a quick review of L'Hopital's rule. When we have a limit of one value as it approaches another, and then we have two functions, one in the numerator, we'll call it f of x, one in the denominator, g of x. Now, as that value approaches the other value, we find that if we take the derivative of each one, that can also give us an answer in case that we have something that doesn't make sense in the numerator and the denominator. And we know these to be infinity over infinity, which we haven't really seen here, but here's one, 0 over 0. Now that's something that looks a lot more familiar with what we've been working with. So now let's take the original equation and let's manipulate it around so we can try and get something in the numerator and something in the denominator where we can take the derivative of. So we see if we can do the multiply by 1 trick for the quantity of k minus alpha squared on the left side, and then that way we can get the entire equation over the quantity of k minus alpha squared. If we keep playing around with it and we take the derivative, which is down here, a little bit of a messy equation, but once you take the derivative of this and you distribute, you'll find that this is the actual final equation as limit of k approaches alpha squared. We take this function and we plug it into Desmos. And just with the value of alpha equaling 1, we can see that this equation looks very similar to the one that we had earlier where we had k equal 1 and alpha equals 0.999. And we see that they're basically without a damping coefficient. And as these two frequencies approach each other, that we see amplification. We see the resonant frequencies of this bridge causing it to sway more and more and more, basically as a function of itself. And so when this starts to happen, it's never going to rectify. It's going to keep on oscillating more and more and more until eventually the structural components of the bridge will not be able to stand the oscillations and the change in position, and the bridge will ultimately collapse. So if we think back to our original equation where we had a b equals 0, a damping coefficient equaling 0, we can basically assume that the bridge was underdamped the whole time. And we know from this bridge that it was very long and very narrow when it was built. And so this was already a concern as it was being built. They didn't know that it would cause the bridge to collapse in the way it did. But with a 42 mile an hour wind speed, this outside forcing function started to cause oscillations within the bridge. Now, because the bridge was underdamped, and maybe just by freak coincidence that 42 miles an hour wind speed happened to be the right wind speed to cause this type of amplification, this type of resonant frequency, it caused the bridge to oscillate more and more, and eventually that is what caused the collapse of the Tacoma Narrows Bridge. Thank you very much for watching and have a great day.